Our Chapter 6 Video 3 is called Reaction Yield and Percent Yield. Anytime we discuss the yield of a reaction, we're talking about the amount of product that's produced. The percent yield can be calculated using this equation, which says that the percent yield equals the actual yield divided by the theoretical yield times 100%. The percent yield is a way to quantify how well reaction conditions work for a reaction by comparing it to the maximum amount of product that can be achieved. The higher the percent yield is, and it will max out at 100%, the higher the percent yield is, the more actual yield is produced with the reaction conditions, and so the better the reaction conditions are. Now, the actual yield will hardly ever be equal to the theoretical yield to give a 100% yield. The actual yield is most often lower than the theoretical yield because a lot of things can happen in a reaction that will decrease the amount of product produced. These things can be low reaction temperature or just unoptimized conditions in general. They can be side reactions, or even things like spilling can cause the actual yield to be lower than the theoretical yield. Now, in terms of what these values are, actual yield is something that can be calculated in the lab, but in terms of a problem that we do in class, it's something that we will either solve for as a variable, or it's something that we are given in the problem. And theoretical yield is something that we can solve for using the stoichiometry steps we learned in the previous video. For any given amount of reactant, we can use that starting amount of reactant to calculate the maximum amount of product that can be achieved. And so that's what we'll do in the next few questions. I just want to reiterate that these yields are in terms of a product. And another important thing to point out is that the yields need to be in grams. So what you plug into this equation should always be grams. It will never be moles of that product. So let's do some examples. What is the percent yield of the following reaction if 60 grams of calcium carbonate is heated to give 15 grams of calcium oxide? According to the equation, 1 mole of calcium carbonate decomposes to yield 1 mole of calcium carbonate and 1 mole of carbon dioxide. The first thing to do in any percent yield or reaction yield, or in general any stoichiometry problem, is to make sure the reaction is balanced, because using mole-to-mole conversions, if your reaction is not balanced, you're not going to get the correct answer. Here we can double check. It seems that the reaction is balanced, so we can continue. Well, what we're going to do is try to decipher what we're given. We're told that we have 60 grams of calcium carbonate, and it's heated to give 15 grams of calcium oxide. Calcium oxide is our product, and so this yield of our product is the theoretical yield. Oops, excuse me, it's the actual yield. So the actual yield of CaO is 15 grams. Now, you're almost never given the theoretical yield in a problem like this. In order to find the theoretical yield, we need to take our number of grams of reactant and figure out what is the maximum amount of calcium oxide that can be created with that starting amount of reactant. Then that will be our theoretical yield. So that's what we have to solve for, and then we'll plug the information into the percent yield equation to find the percent yield. So, solving for the theoretical yield, We'll start with those 60 grams of calcium carbonate, and here are our steps. We're going from grams of CaCO3 to moles of CaCO3, and the conversion factor there will be 1 over the molar mass of calcium carbonate. Then going from moles of calcium carbonate, we will convert that to moles of our product, calcium oxide, using the mole ratio. And finally, to get the mass of calcium oxide produced, we will convert from moles to grams of calcium oxide using the molar mass. Alright, so let's set up our conversions. We start with the 60 grams of calcium carbonate. We convert that to moles. I calculated the molar mass of calcium carbonate previously, and I found that it's equal to 100.09 grams, which will go on the bottom, and then that 1 mole of calcium carbonate on top. So the grams cancel out. Now we're in terms of moles of calcium carbonate. To cancel those moles out, we need to use the balanced chemical equation to find the mole ratio. We have 1 mole of calcium carbonate for 1 mole of calcium oxide. So we have a 1-to-1 mole ratio. So numerically it won't make a difference, but I'm still going to include it so we see how those units cancel out. 1 mole of calcium oxide on top, 1 mole of calcium carbonate on bottom, which will then cancel out. Now we're talking about moles of calcium carbonate, and to get to grams, we use the molar mass, which is found to be 56.08 grams. I'll put those 56.08 grams on top, the 1 mole of calcium oxide on bottom. Moles of calcium oxide are gone, and now we're left with our units grams of calcium oxide. So grams of our product. When we do the calculations here, 60 times 56.08 divided by 100.09, we get that the theoretical yield, which I'm going to write up here, is equal to 33.6 grams of calcium oxide. So starting with the 60 grams of calcium carbonate, according to the stoichiometry of the reaction, that's the maximum amount of calcium oxide we can get. So in order to figure out what our percent yield is, we will plug in our numbers. The percent yield equals the actual yield, which is 15 grams. So that was the amount of calcium oxide that was actually isolated as a part of this reaction. 15.0 grams of calcium oxide divided by the theoretical yield, which is 33.6 grams of calcium oxide, multiplied by 100%. We get slightly below 50%. We get 44.6% as our yield for this process. Let's do another one. What is the percent yield of the following reaction if 77 grams of calcium cyanide in excess water produces 27.1 grams of ammonia? Again, deciphering what we have 77 grams of calcium cyanide, which is a reactant, and we're told that it produces 27.1 grams of ammonia, which is a product. So right off the bat here, we can say that the 27.1 grams of our product is the actual yield. I'm just going to write actual Y. And now we're also told we have excess water. When you have excess of a reactant, that means that you don't have to worry about it. And so it doesn't limit the reaction, which we'll talk about in the next video. So we're just not going to worry about water right now. In order to find the percent yield, we need to calculate our theoretical yield, So we need to find what is the maximum amount of our product ammonia that we can get with 77 grams of calcium cyanide. So let's solve for that right now. I'm going to say that our theoretical yield, or Ty, is equal to this. Now we're going to follow the same steps as before. We'll start with our grams of calcium cyanide, and we'll go to moles of calcium cyanide using 1 over the molar mass. Then we'll go from moles of calcium cyanide to moles of ammonia using the mole ratio from the chemical equation. And then we'll go from moles of ammonia to grams of ammonia using the molar mass. Now, we need to make sure that the chemical equation is balanced. So double checking, just always make sure to double check. 1 calcium, 2 nitrogen, 6 hydrogen, and 3 oxygen, and 1 carbon. So it looks good. We can proceed. We'll start with our grams of calcium cyanide that's given to us in the problem. 77.0 grams of CaCN2. The molar mass of calcium cyanide is, let me see here, the molar mass of calcium cyanide is 80.11 grams, and so per 1 mole. So I'm going to put that 80.11 grams on bottom so they cancel out, CaCN2, and put that 1 mole of CaCN2 in our numerator. Now grams of calcium cyanide cancel out. We've used the molar mass as a conversion factor. Our next conversion factor we'll use is canceling out moles of calcium cyanide to get to moles of ammonia, which will use the mole ratio from the balanced chemical equation. Up here we see that there is 1 mole of calcium cyanide needed to produce 2 moles of ammonia. That means that we'll put that 1 mole of CaCN2 on bottom and the 2 moles of NH3 on top. Moles of calcium cyanide are gone, and moles of ammonia are now what our units are in terms of. To convert from moles of ammonia to grams of ammonia, the conversion factor used is the molar mass. The molar mass of NH3 is 17.04 grams per 1 mole. So I'm going to put that 1 mole of NH3 down here and the 17.04 grams on top. Now everything that we don't want has canceled out. Grams of calcium cyanide, moles of calcium cyanide, and now moles of ammonia. Our answer has the units grams of NH3, and it is equal to 77 times 2 times 17.04 divided by 80.11, and that equals 32.8 grams of NH3. Now this again is called our theoretical yield. It's the maximum amount of ammonia we can get by reacting 77 grams of calcium cyanide in excess water. Now to find the percent yield, we use that equation. We're going to say that the percent yield is equal to our actual yield, which was given to us in the problem, 27.1 grams of ammonia, divided by the theoretical yield, which we just solved for. It's 32.8 grams of ammonia, and we'll multiply that by 100%. So notice how our grams cancel out here in the percent yield equation, and our answer is just in terms of the unit percent. 27.1 divided by 32.8 times 100% is equal to 82.6%. So a really good yield for this reaction. Alright, one more problem, and it's a little bit different this time for this video. Here we're asked how many grams of carbon dioxide are actually produced if the reaction of 40.8 grams of C6H6O3 reacted in excess O2 gives a 39.0% yield. Now this is the other type of question that can be asked regarding percent yield. We're asked how many grams of carbon dioxide, a product, are actually produced. So we want to solve for the actual yield. We're given the percent yield, 39%, and we're given a mass of our reactant. So what we need to do here is set up the equation like this. Given the percent yield of 39.0%, this equals our actual yield over our theoretical yield times 100%. Here we need to solve for the theoretical yield as we have been previously, and then plug it into this equation and solve for the actual yield. So let's solve for our theoretical yield of carbon dioxide, CO2, starting with our amount of C6H6O3, 40.8 grams. Now the molar mass of C6H6O3 is 126.02 grams per mole. That's what we'll use as our first conversion factor, starting with the number given to us in the problem, 40.8 grams C6H6O3, and using the molar mass of this compound. We're going to put the grams on bottom. That 126.02 grams goes on bottom, and the 1 mole of C6H6O3 goes on top. Grams cancel out, and now we're in terms of moles. We need to get from moles of this compound to moles of carbon dioxide. So we're going to put use the balanced chemical equation. We have a 1 to 6 mole ratio, so I'm going to put the moles of our reactant on bottom, 1 mole C6H6O3, so they cancel out, and then our 6 moles of CO2 on top, so that they don't cancel out. And finally, convert from moles of carbon dioxide to grams of carbon dioxide using the molar mass. In 1 mole of carbon dioxide, there are 44.01 grams. Now moles of carbon dioxide are gone, and our units are grams of carbon dioxide. Numerically, this answer equals 33.3 grams of carbon dioxide. Oh, nope, it's 85.5 grams. Taking 40 times 6 times 44.01 and dividing by 126.02 should give us our 85.5 grams of CO2. Now we need to find how many grams of carbon dioxide are actually produced by using our theoretical yield in our expression that we wrote earlier up here, this guy that I'm circling. And so we'll just plug the 85.5 in for our theoretical yield, rearrange and solve for actual yield, and we should have it. Alright, so our 39.0% equals the unknown actual yield divided by the known theoretical yield, 85.5 grams, times 100%. So what we're doing to solve this is dividing 39% by 100% and then multiplying that product, or that, what would it be, quotient, by 85.5 grams, and that gives us our actual yield of 33.3 grams of carbon dioxide. So that is how many grams of carbon dioxide are actually produced in this problem.